Components of a vector. Okay, so in our previous video lectures, we looked at adding vectors, and we did it graphically using a ruler and in some cases a protractor. And we noticed that accuracy could be a little bit off. It was a nice approximation, but it wasn't very precise. So we're going to learn in this video and a couple of upcoming videos how to be more precise when we add up our vectors. In this lecture, our objective is fairly simple. We want to find the x and y components of a vector. All right, let's pull in some things that we already know that are going to be useful in this video lecture. Here's what we're coming in with knowledge of. We know that given a right triangle, the sine of an angle, theta, is equal to the opposite leg length divided by the hypotenuse length. And we know that the cosine of an angle is equal to the adjacent leg length divided by the hypotenuse length. Let's just pull a quick picture in here, remind ourselves our basic trigonometry facts. Here is a right triangle. Here's an angle theta. This is called the long side, the longest side of the right triangle. The leg that is opposite the right angle is called the hypotenuse. The leg opposite the angle, here's the opposite leg, and then the side next to it is called the adjacent. Okay, the adjacent one. So sine of theta, opposite over hypotenuse. Cosine of theta, adjacent over hypotenuse. And let's note a bit of algebra. Okay, if we take this equation and we multiply both sides by the hypotenuse, we'll come up with the fact that the opposite leg length is equal to the hypotenuse, and I'll abbreviate at HYP, times the sine of the angle. And we can do the same thing with the cosine, multiply both left and right side by the hypotenuse, and we can determine that the adjacent leg's length is equal to the hypotenuse times the cosine of the angle. So that's stuff we come in knowing, and it's going to be useful in this video lecture. All right, so let's talk about what are components of a vector. Well, components of a vector are the vectors that are added together to create a resultant vector. Okay, so here is a resultant vector. And we can say, okay, how do we get that vector? Well, we added up this vector. I'll draw it a straight line, kinda. We added up vector A, and we added that to vector B, and we got vector R, the resultant vector. And of course, vector A could have been this way, and then up to B. Vector A could have been this way, and then B could have been this way. There are an infinite number of ways to get this resultant vector. You could have 2 or 3 or 4 vectors. We're going to focus on 2, and we're going to focus on vectors in the x direction and the y direction. But as far as our definition is concerned, vector A and vector B are components of vector R directed at the angle theta. Okay? Okay, so that's what components are. All right, let's take a look at how this might work. In terms of what we want to do with these components. Okay, so now we're going to pull in, we're going to relate, let me slide this back down. Now we're going to kind of relate our trig information with what components are. Okay, let me get this straightened out, I hope. Okay, to relate trigonometric functions to vector quantities, we place the vectors in standard position. Okay, standard position for a vector means the initial point of the vector is at the origin of the rectangular coordinate system. Okay, so I have a rectangular coordinate system, and we'll have the initial point of every vector at the origin right here. Okay, this allows us to find the vectors x, which is the horizontal, and y, which is the vertical components. Okay, finding these x and y components is called resolving the vector into its components. And I want to point out that really from this point forward, when we use the word components, we're meaning the x and y components. So those get kind of interchanged sometimes, but generally you'll just see, hey, what are this vector's components? And you want to be thinking we're looking for the x and y components. We also want to note the angle theta is always measured from the horizontal. Okay, so I will draw a vector A. There's vector A. And here is theta, measured from the horizontal. And if I drop down to here, then this vector, and I'll bold it so you can see it, this vector is its x component, vector A sub x. And if I come over to here, and again I will kind of bold it so we can see it, this is vector A's y component, so it's vector A sub y. So we have resolved this vector into its x and y components. So vector A is the same as its x component plus its y component. And this is nice because once we know the x and y's, we can substitute whatever this vector is with this sum, and we can do math with it. Okay, let's remind ourselves some more trig knowledge that we have. The cosine, okay, so let's go back to what we learned earlier. The cosine of this angle, cosine of course is opposite over hypotenuse, and so we have, that would be cosine, adjacent over hypotenuse. Sorry about that, cosine is adjacent. So it is a sub x over a, okay? Cosine, the adjacent side over the hypotenuse. Now notice I didn't put arrows over here. I'll discuss that in a second, but a non-arrow letter represents magnitude, not vector. And this tells us that the length of the a sub x vector is equal to the length of the hypotenuse, or the original vector, times the cosine of theta. And we can do the same thing with sine of theta. The sine of theta is equal to the length of the opposite side, okay, a sub y over the length of the hypotenuse a, which means that the length of the opposite side, the length of the vector in the y direction, is equal to the length of the original vector times the sine of theta. Okay, this is going to come back time and time again. Okay, we may change it to an R and an R or something, but this is going to be, you might put a box around that. We're going to make use of this relationship often when we deal with vectors. Okay, so a note on notation. Okay. A vector, so we say vector A has magnitude or size A. All right, so now of course I wrote it with an arrow above it. It can also be written boldface when I type it, but this indicates a vector, and this indicates its magnitude, its length or its size. Okay, so let's just see here. So we do if the letter is in boldface type or with an arrow above it, right? An arrow above. This tells us it's a vector. Okay, if the letter is in lightface type, non-boldface type, this tells us that we're dealing with its magnitude. Okay, so we're going to want to know that notation. Work with that. The vector is indicated with an arrow above it, or in boldface. If there's no arrow or it's not in boldface, we are dealing with its length, its magnitude. Okay, let's take a look at some examples and work with this here. Maybe that'll help to clarify this a little bit. I think I got my screen set up. Okay. Resolve the vector A into its x and y components. The magnitude of A is 7.25. Okay, so here is the vector A. Magnitude is 7.25. Okay, so its components, its x and y components. I'll do this too for 62 degrees. This is the vector A sub x. And I'll come over to here. And again, I'm trying to draw it bold so you can see it. Whoops, that was off. Sorry about that. This is the y component, A sub y of the vector. Okay, so we know here, now remember, A, which is the magnitude of vector A, is equal to 7.25. Okay, so x component, and we're looking for its length. What is the length of vector A sub x? Okay, the magnitude of the vector is equal to the magnitude of the given vector times the cosine of theta. So the magnitude of the A sub x vector is equal to, well, the magnitude of this vector is 7.25 times the cosine. The angle is 62 degrees. Let's put that in the calculator. You want to be careful for those who maybe are in a TI calculator or something that you're in degree mode. You can see on my calculator I'm in degree mode right up here. If not, I need to go into mode. And this is the degree line. This is the radians or degrees. I need to be in degrees. Okay, so what is 7.25 times the cosine of 62 degrees? And I came up with 3.4. We'll go to the 10th place. 3.4. Okay, the y component. So again, the components are the magnitudes of the x and y vectors. Okay, the magnitude of the y component is equal to the magnitude of the vector times the sine of the angle. Okay, so again, the magnitude of the vector was 7.25. The angle's measurement is 62 degrees. And I've already done the math, and it came out to be 6.4. Okay, so resolve it into its components. Let's make a note of what this means. The x component is directed along the x-axis to the right because it's positive. We got a positive number. It's directed to the right and has magnitude 3.4. Magnitude or size. the y component is directed along the y-axis, and we're positive, so we're going up. So I'll say upward, and has magnitude 6.4. Okay, let's look at a couple real-world problems, real-world situations, or real life situations. Okay, a surveyor's marker is located 14.4 meters from the set pin at 126 degrees standard position. Find the components of the displacement of the marker from the pin. Okay, when we say an angle is in standard position, we want to remember that means that this angle is measured counterclockwise from the positive x-axis. So I'm going to do a quick little, I'll do a quick x and y here. All right, we'll go this way. Okay, so there's my x, there's my rectangular coordinates. 126 degrees, well this is 90. This is 90, this is 180, so I got to be somewhere around here, 126. I'm not going to worry about a protractor at the moment. I'm just going to go like this. And I'm going to say that this is 126 degrees, and this is 14.4 meters. And so let's see, the set pin, this is the marker right here. This is the marker. And this is the set pin. So a marker is located 14.4 meters from the set pin at 126 degrees standard position. There we go. Okay, so now we want to find the components. I'm going to go ahead and draw it again so I don't make my diagram my diagram is not overly busy. I think I can get it pretty accurately. X and Y axis. That's how far is that? About one something or other. I'll go out to here. So this is the vector I'm after. This is 126 degrees. Okay. Now, this is the y component, the x. So if I call this d, this is vector d for distance, then this is the vector d sub x. That's its component there. And then I can go across to here, and this is going to be the y component vector right here. D sub y, okay. There we go. So we have that, and we want to find its displacement. We want to find the components. Okay. All right. So what do we know? The magnitude of d sub x is equal to the magnitude of the given vector. Again, we don't have any arrows over these, times the cosine of theta. Okay, so let's see here. This is the x component. I should have written that down first. Sorry about that. The x component. Okay, so again, let's make a couple of notes here. The x ties us into the cosine. Notice that our angle, of course, is in standard position. And these two letters are magnitudes. There are no arrows above them. And so we're off and running with substitution. The magnitude of the x component The distance is 14.4. The cosine, the angle in degrees is 126 degrees. I've already done this with my calculator. You can do it with yours. And I came out with negative 8.46 meters. Let's do the y component. Okay, so d sub y is equal to d sine theta. And let's see here, d sub y is equal to, well, the distance is still 14.4. And now we use sine. The standard position angle is still 126 degrees. Again, I've already put this in my calculator, and I came out with 11.6 meters. Okay, so in words, the x component is directed along the x-axis, of course, is the x component. And this time, because it's negative, it's to the left, not the right, to the left, and has magnitude 8.46. And the y component, let's see, the y component is again directed upward because it's positive. Upward along the y-axis, of course, because it's the y component, and has magnitude 11.6. I guess I should include the units because we're dealing with units. I'll put the meters here and here. So there you have it. Up a little bit low. I'll come up a little bit. There you have it. In more of a real life situation, if you will. Let's do one more. Need to change papers. Okay, so I can get this on your screen there for you. There we go. Oops, not quite. That's better, I think. Okay. A car is being unloaded from a ship. It is supported by a cable from a crane and guided into position by a horizontal rope. If the tension in the cable, this is the cable here, is 2,790 pounds, and the cable makes an angle of 3.5 degrees with the vertical, what are the weight of the car? We want to find this. And the tension in the rope. We want to find that. Notice those are both magnitudes. Weight and tension do not have direction. So we're looking for their magnitudes. Well, notice the tension is in the x direction. The weight, we're in the y direction. Okay. And we want to note here, don't forget, we talked about this earlier, your angle must be measured from the horizontal. This is measured from the vertical, so that's not going to work. So let's go across here, and let's measure it from the horizontal. Well, this is a right angle, of course, so we'll do 90 minus 3.5, and we come up with 86.5 degrees. So we want to make use of this because it's from the horizontal. Okay, so I'm going to redraw this. Okay, I'm going to kind of redraw this as a triangle using this angle instead. So this point is the same. My cable, this is still the cable, so I'm still down to here. That's here and here. Okay, I'm just going to simply draw it this way. There's the right angle. Oops, there's my right angle. This is my theta right here. That's my, I'll tell you what, let's go in here. Let's put this as my 86.5 degrees. And the weight is in the Y direction, and the tension is in the X direction. Tension in the X, weight in the Y. Let's use this. Okay, let's use this instead. We'll use this so we have the angle measured from the horizontal. Okay, so the weight. The weight is, looks like I'm doing, it says, yeah, find the weight and the tension. Well, the weight is in the Y direction, so we'll do Y direction first in this case. Okay, the magnitude, the weight is equal to the, okay, we know it's the hypotenuse times the sine of the angle. Okay, so the weight, the hypotenuse is, well, this is 2790 right there. So the magnitude of the cable, the magnitude of the given vector is 2790. The angle measured from the horizontal is 86.5 degrees. I've already put this into my calculator, and I came out with a weight of a car of 2,785 pounds. Okay, hope I got that right. Now let's do the tension. The tension is in the X direction. So we got that one we're calling T. And we know that in the X direction, it's the hypotenuse. If I could ever learn how to write my Y's, I'd be in good shape. Times the cosine of theta. Well, our hypotenuse we know is 2790. That's the magnitude of the cable. The angle from the horizontal is 86.5 degrees. Make sure your calculator or your device is in degree mode. And I came up with 170 pounds. Okay? 107. Whoops, a little bit off. Let's go back. Make sure you can see. There we go. So there's, sorry about that. I think I didn't move my screen up very well. So there's my tension and my weight. Just a note here. Okay, in real life examples, so this is obviously kind of a nice physics example. Magnitudes, they're going to be positive. They're generally positive. You know, we don't say we have a negative weight, okay? So we're often dealing with, positive acute angles measured from the horizontal. Maybe not always, but in general, we're doing, general real life stuff that's kind of positive in general. So you want to think about that. So there you have it. A little bit of work on how to find the X and Y components of a vector.